So in the last classes, we have already covered the definition of vector spaces. Now we know what these quantities are. We have also talked about linear dependence and independence. And we've also talked about inner product spaces. So in this class, we'll talk about linear transformations. And as you would see that the matrix system, the system of linear equations, when you write the matrices that you get are essentially also a form of linear transformations. So what are linear transformations? Linear transformations are essentially mappings. They are linear mappings. They map one vector space, let's say V, to another vector space, let's say U. So that's what they do. They are linear mappings, okay, in a spatial way. Now, if you look at the definition of what transformation you would call as a linear transformation, you would see that if we consider two vector spaces, V and U, then the linear transformation is a function which is mapping V to U in the following way. So if you take two vectors and add them up in the vector space V, so this addition is taking place in the vector space V, and you do the mapping. You do the mapping. Let's say the mapping is denoted by this symbol. Then this is going to be same as if you would have mapped a single vector U and then added it to the mapping of the vector V. And this addition that is taking place is of course taking place in the vector space U. So this addition that you saw here is in V, and this vector addition that is taking place is happening in U. And this is true for every U and V of the vector space V. So this is one part. Second is if you scale a vector with lambda and then do the mapping, I should have used the same symbol for the mapping. Let's say the mapping A. Then it is same as you first do the mapping of U and then scale with lambda. Now this says something about the field, this scaling that you have done, which is essentially this lambda belongs to the field F, right? So this also says the kind of mappings that can take place. So it means that when you define the vector space V and the vector space U, they're sharing the same field. So the triple V, F, and the spatial function F is also there in U, F, and this way. That thing you have to keep in mind, and that's when you get this property for the linear transformation also. Right? So now if you combine these two conditions together, you can write it as one condition that you have to look for when you're checking for linear transformation. And that condition is given by if you scale and add two vectors in this form, lambda times U plus mu times V, then this is same as sort of mapping and then scaling. Mapping and then scaling in this addition that is taking place in the vector space U, and this addition is taking place in vector space V. The numbers lambda and mu, or the parameters lambda and mu, they belong to the field F. Okay, and this is true for every U and V in the vector space V, not for some. It's for every vector in V should satisfy this. Then we call A or as a linear transformation or a mapping if you prefer. It's a mapping, it's a linear mapping. Now, the interesting thing, another property that is required is, so you could have chosen lambda as 0. So then you would get essentially A times lambda is 0. So 0 in B is essentially lambda, which is 0 in U, which means that the 0 of V is going to get mapped to 0 of U. That's a condition. That's what linear transformations do. They map 0 to a 0. That's another condition of linear transformation. Now, let's say if you had a collection of uh, vectors, a set of vectors, v1, v2, and then you're sort of doing the mapping. So you can think of, suppose if you had taken v1, v2, v3 as a set, and then you sort of chose to write your vector v in terms of vi's. Now, this vi's may not necessarily be the basis of this vector space. It's just some set we are taking. And you can represent another vector v which belongs to the vector space v in this form. Now, the mapping A of v would look like this. So it will be lambda summation lambda I A of vi. That's what A of v is going to be. Correct? Now, suppose if this set that you have taken, is a linearly dependent set. In that case, if this is a linearly dependent set, which means that for non-zero values of lambda I, this equation is satisfied. That means satisfied. That means there are non-trivial solutions to lambda I. Then A times lambda summation of lambda I vi. Now that we know that it can be written as summation of lambda I A vi, and let's say the ui is A vi, and if you write it like this, then you get summation of lambda I ui. Now you're saying that this is 0 because of this equation A of 0, and it is getting mapped to 0. And then you get this is equal to summation of lambda I ui, right? Means uh, a linear combination of the vectors ui's is giving you a 0 for non-trivial values of lambda I. That's what we started with. This is true for non-trivial values of lambda I, and then those lambda I values have been carried through these equations, and finally you get summation of lambda I ui is also equal to 0, which means that the set that you have taken uh, of AV1, AV2, AVN after the mapping also forms a linearly dependent set. Now this implies uh, that a linearly dependent set maps to a linearly dependent set. Okay. But if we take this V1 to Vn as a linearly independent set, then we cannot say clearly. If you follow the above steps, then you cannot say, because the above equations are going to be satisfied trivially for the trivial values of lambda I, and in that case this equation would also hold, but then you cannot say anything about the vectors u1 to un. Okay, so you cannot state any properties, although v1 to vn are linearly independent, but you cannot say anything about the mappings, whether that will turn out to be linearly independent or not. Okay, so you cannot say. The reason is that you can have the mapping could be a many to one mapping. That means more than one vector gets mapped to the same vector in U. So AV1, let's say, is U, then AV2 is also U. In that case, the final set that you will get, U1 to UN, can be linearly dependent. Now, it's also possible that one of the vectors is getting mapped to 0. So if abj is 0, then the final set that you get of u1 to u1 to u1 u2, and then there is a corresponding to vj, the mapping is 0, and then you have this. Now clearly a set which has 0 in it is a linearly dependent set. So this will form a linearly dependent set, right? So now this brings us to the definition of kernel space. Okay, this is a subspace of V, and it is defined in a fashion that it's a set of this kernel space. Prove that it's a subspace later, but for now we'll just look at the definition, what it is. So kernel space is the set of all the vectors in V which map to 0 of U. So this kind of a space is always defined with respect to a given linear transformation, because we're talking about both V and U in the definition and the mapping. Right? So for a given mapping, the set of vectors that will map to 0 is called the kernel space. In other words, you can write this in this fashion. So K of A is equal to a set of all the vectors V such that A of B is 0. Now, in that, so kernel of A is a subset of V that we know, but can we sort of say whether it's a subspace? For that, we'll have to check those two properties that we had put. One is the closure. Both of them are essentially the closure properties. One with respect to scaling, another with respect to addition between the vectors of the set. So now let's say if we take some vector v which belongs to k of a, and then let's say whether we want to check whether lambda v also belongs to k of a. That's what we want to check. So we follow the procedure of the mapping, the properties of the mapping is what we're going to use here to show this. So if a of v is 0, then a of lambda v is lambda times av. Now av is 0, so you get 0. That means if v belongs to k of a, then clearly lambda v will also belong to k of a. That's very clear now. If we take two vectors which belong to k of a, let's say v1 which belongs to k of a and v2 which belongs to k of a, then av1 is 0 and av2 is also 0, because that's the definition of k of a. Now if we add them up, v1 plus v2, will that be also getting mapped to 0? So now again we use the property of linear transformation that a of v1 plus v2 can be written as a of v1 plus a of v2. Both of them are 0, so you get a 0. And this 0 belongs to u, of course. Right? Now, which means that v1 plus v2 also belong to the kernel space k of a. This proves that kernel space, or the set of all the vectors which map to 0, is a subspace of V. Okay, and we call it the kernel space. Another name that you would remember from the matrix theory is the null space. So this is same as the null space. Now we can define nullity as the dimension of this subspace, dimension of nullity, the dimension of a null space is going to be less than or equal to dimension of V. Now, if you take the mapping A, which is mapping everything, it's a zero mapping. If you take V to U such that A of B is equal to 0 for all vectors V belonging to the vector space V, in that case, the equality will hold. In that case, you would have dimension of the kernel space being equal to dimension of V. That's a very special case of zero mapping, which maps everything to 0. Now we can, as I was talking earlier in the previous class, that classes, that Venn diagram is the best way to represent these sets. And for linear transformation, it's very useful, again, for picturing these mappings. Now let's take two subspaces, two vector spaces, V and U. Okay. Now these can be the same spaces also. So U can be V. Okay, this can be like mapping from the vector space V to a vector space V. That's possible. But here for general case, we'll take a mapping from V to U. Now, what is kernel space? Kernel space is a sort of subspace which will map everything to 0, right? And away from it, all the vectors will get some map to some vector in U, correct? Now, if you take the mapping of all the vectors in U, so these are all the vectors that have been mapped from V. So these are they are mappings of vectors V using A, some linear transformation A. All right. Now the set of all these vectors will form range of A. I'm calling it as a set of vectors. Later we'll in a bit we'll show that this set of vectors also forms a subspace, and this will be a subspace of the vector space U, clearly, as you can see from the Venn diagram. Now, so we can, if it's a subspace, then you can define a rank also. The rank of this subspace is going to be the dimension of this subspace. Okay, that's what you call the rank of a matrix, essentially the dimension of range of A. Okay, the same concept, with using the same concept, you can define rank of a range of A of a linear mapping. So to show that this range of A is actually a subspace of U, what you do is this is the way formally how you will write range of A. Range of A is essentially collection of all the vectors that have come from mapping of a vector V in of all the vectors V that belong to the vector space V. Okay, so now to show this, we'll again use the property, the definition of the linear transformation. We say if AV1 belongs to the range of A and AV2 also belongs to the range of A, then AV1 plus AV2, which is nothing but A of V1 plus V2, and V1 plus V2 is a vector V which belongs to the vector space V. So again, it's a linear mapping. That means A times V is getting mapped to AV1 plus AV2. That means AV1 plus AV2 also belongs to range of A, right? Now, if we take a scaling of a vector, so if we say AV1 belongs to range of A, then the lambda times AV1 should also belong to range of A to call range of A as a subspace of U. So we scale it with lambda and check, and again use the property of the linear transformation and send lambda inside. Now becomes lambda times V1. Now this again is a vector V, which is a vector of vector space V. So so this from the linear mapping, this again is going to belong to some range of some vector of range of A. Clearly, these two properties are satisfied, and therefore we can call now range of A as a subspace of U. So range of A is a subspace of U and not V. U. Kernel space is a subspace of V. Range of A is a subspace of U. Dimension of range of A, as you can guess, because it's a subspace of U, will always be less than equal to dimension of U. Okay. Now what we do is, let's take an arbitrary vector. Let's call this vector V, which belongs to the vector space V. Now we can represent vector V as a linear combination of some vectors which are linearly independent. Now we are taking this set as linearly independent. In fact, what we're taking is we're looking at the bases of V. So this is like one of the bases that we have picked for the vector space V. And given by the number of vectors that are there in the basis, the dimension of V is n. Okay, let's say. And now what we do is we say, because kernel space is a subspace, we can define this basis such that the first k vectors v1 to k vk, and those vectors span the kernel subspace. Okay. So the first we have defined the bases in this fashion. So we are saying v1 to vk, they are spanning the kernel space. That means we are saying the dimension of the kernel space is k. And we are saying, let's say for a given problem, that's the case. K can be 0, k can be n. K will be n for a 0 mapping, if A is mapping every vector to 0. Now, you say A of V, again, we can write A of V as summation lambda I, AVI. And now, because the first k vectors in this summation are going to get mapped to 0 because they belong to kernel space or null space. So A of V will essentially be I from k plus 1 to n. So that's what your mapping will look like. Any mapping, any AV mapping. Other vectors are getting mapped to 0. Okay. So any vector, now u, which is part of the range of A, is essentially spanned by, can be represented as a linear combination of AVI, where I runs from k plus 1 to n. So this essentially spans range of A, right? Now, from this set, we can say clearly that there are no two vectors that will map to the same vector. Okay, that means from this set, let's say AVK plus 1 to AVN, you will have no vector which will get mapped to the same vector u. So none of them would be something like this gets mapped to, let's say, u1, and then there is another vector which gets mapped to u1. This will not happen. To show this, let's prove this by contradiction. So what we do is we say, let's say a alpha times avk plus 1 is getting mapped to some u1, and beta times avk plus 2 is getting mapped to u1. Okay, let's say two vectors getting mapped to the same vector in U. So now we can write these two equations, subtract them, and that will reduce to this one single equation, which is A alpha times Vk plus 1 minus beta times Vk plus 2 equal to 0. Now we know that if it is getting mapped, if this vector is getting mapped to 0, then this vector must belong to the kernel space, right? That means alpha Vk plus 1 minus beta k plus Vk plus 2 is essentially a vector from the null space V1 to Vk. In that case, we should be able to write alpha Vk plus 1 minus beta Vk plus 2 in terms of vectors V1 to Vk. But then V1 to Vk are the first k vectors of the same set which is linearly independent, which means that we cannot write Vk plus 1 or Vk plus 2 in terms of V1 to Vk. We cannot do that. So it cannot be a part of the kernel space in that case. So we get a contradiction. So which means that AVK plus 1, and this also would be a linearly independent set in U. Correct? So now, which means now from here, because it's a linearly independent set and this is going to span range of A, then the number of vectors in this maximum linearly independent set will give you the dimension of range. So the dimension of range then can be given by n minus k. From this, we conclude that dimension of V, which was n, is equal to dimension of k, kernel space, which is k, and dimension of range of A, which is n minus k. Okay. Now, if it turns out that there is only one vector, zero vector, only zero vector is getting mapped from V to U, from the zero of V to zero of U. In that case, so I'll rephrase myself. If you have only one vector which is getting mapped to zero of U, in that case, kernel space would have only one vector, zero, and the dimension of the kernel space will be zero. In that case, it will turn out if you took a basis V1, V2 to Vn, if this was your basis, this was basis for vector space V, then the basis for the vector space U is going to be not for U, basis for range of A will be this. Now you could be a bigger subspace, and you could be mapping only to a smaller part of it. That's why this will give you basis for range of A only and not necessarily of U. So if you take any vector V, if this is true, then it will map to only one vector in U. Okay. So you take any vector V, then it will get mapped to only one vector in U. And from this, you can also conclude that dimension of range of A is dimension of V. This also comes from the formula that we have already looked at, which is here. Right? This formula also says that if K is 0, the dimension of range of A will be same as dimension of V. These kind of mappings are called one-to-one mappings. When kernel space is zero vector only, then you call such mappings as one-to-one mappings. And the transformation, linear transformation, is called regular transformation. Okay, one-to-one mapping is saying one-to-one mapping is same as saying regular transformation. One and the same thing. Now, if you're mapping to every vector of U, that means the range of U is essentially the entire U, then the dimension of range of A will be dimension of U, right? The mapping in that case is called an onto mapping. That means you're mapping to every vector in U. So every vector in U has an image in. So every vector U of the vector space U has a pre-image in V. Okay. The range of A is essentially the entire set of vectors in U. Now, this does not mean, okay, that kernel space, if you have one-to mapping, it doesn't mean that this is just this. It does not mean this, does not mean that kernel space is this. You can have a smaller V, a bigger V, and a smaller U. Then you will map some of the vectors to 0. Let me do it properly, neatly here. So you can have a bigger set V and a smaller set U, and then you're mapping some of the vectors of V to 0 of U. Okay. And the remaining vectors that you have are getting mapped to the other vectors in U. And so U is essentially range of A. Okay. So your kernel space can be bigger than 0. So k can be greater than equal to 0 still. Okay, but dimension of range of A is same as dimension of U in this case. Now let's sort of take an example. So consider the mapping, which is a mapping from mapping A from R cube, a 3D space, to a 2D space, which is sort of an example of what I just said, that vector space U is of smaller dimension than vector space V. So the mapping is given by these two equations. So x1, x2, x3, they belong to R cube. So the vector looks like this. And y1, y2 belong to R square. So vector y looks like this. Vector y looks like this, and vector x looks like this. Okay. To get the kernel of A, what we do is we look for the mapping to go to 0. That means y1 is 0 and y2 is 0. And then we look for the possible values of x1, x2, x3 for which this will be true. Now clearly you will see that there are more number of variables than equations, so there are infinite solutions of this form. There x1 has to be equal to minus 11 x3 and x2 is minus 5 times x3. So you can get x2 in terms of x3 directly from here, and when you substitute it here, you get 10 times x3 plus x3 11 times x3. That gives you x1 as minus 11 times x3. So you can write this vector x1, x2, x3, this vector in this form: x3 times minus 11 minus 5 1, and you can choose any value of this x3. So you can say alpha times this thing. If you look at the mapping, it will give you a 0. Correct? That means the kernel space A is essentially the span of the vector minus 11 minus 5 and 1 here, right? That's just this. So dimension of the kernel space A is essentially 1. And the dimension of V was 3. So that gives, so if dimension of K of A is 1 and dimension of V is 3, then you get the dimension of range of A, which is going to be 2. Okay, so you can from here say this is an onto mapping because you're mapping the entire R2, right? Because dimension 2 indicates that you're mapping the entire R2 using this mapping, right? So if the kernel, this this set of equations had two solutions, then the dimension of k would have been 2, and in that case dimension of range of A would have been 1, and then you can say that it's not an onto mapping, right? So now we move to something which we call as we're defining these quantities. Okay, we have defined linear transformations. Now we're defining some things, some additional operations for these linear transformations. So we define sum and product of linear transformations. So definition is such that if you're adding two linear transformations and then mapping a vector V, that is same as doing these two linear transformations separately on V and then adding. So this is addition of vectors and this is addition of linear transformations. And if you're talking about these A, B, and as you will see, etc., they are mapping such that they're mapping V to vector space U. Okay, so they are all the same kind of mappings. They're the same kind. They're all linear transformations, and they're mapping V, a vector V, to vector U. Of course, these mappings could be different, and therefore we are denoting them by different symbols. So this addition of vector that is taking place now is in U. Okay. So this is how you define addition of linear transformations. This is definition of the addition of two linear transformations. Now you can scale a linear transformation as well. The scaling of a linear transformation is essentially scaling of the vector. So mapping, right? Of course, this is also something that we're doing in U, but then this is going to be same as also A times lambda V, correct? They're going to simplify, they're going to mean the same thing. Now, this would be an assignment that using the above definitions, you can show that a set of linear transformations from vector space V to vector space U is going to be a linear transformation, it's going to form a vector space based on the definitions of addition and scaling function that we have defined above. Okay, this can be shown. Now we can define product of linear transformation as well, multiplication of linear transformations. Now let's say there are three vector spaces U, V, and W. We're marking them here as three sets on a Venn diagram: vector space V, vector space U, and vector space W. These are three vector spaces, and there is a set of linear transformations. Let's say A is a linear transformation. A belongs to set of linear transformations from V to U. Okay. Whereas you take another linear transformation B, which is a linear transformation, which is from the set of linear transformations which are mapping U to W. Right? Then you can think of it as, okay, there was a vector V which got mapped to U, and then using this transformation B, you mapped it to another vector W, right? Now, what you can do is you can define another mapping, which let's say call C, which now belongs to a vector space V getting mapped to W directly. So we can map it directly to W using this C. Okay. So now, if this is the nature of the mappings, then you can say C is nothing but a product of the mappings B and A. Okay. The reason why we write it as BA and not AB is the following. So this essentially the way you write will define the order of these operations, of these mappings. So let's say if you have B, A, and it takes a vector B, okay, and it gives you a vector W, right? That's what this means. You can also split it into pieces. You can say B is essentially A times V, A operating on V, or A mapping V and giving a W, which you can write as B, U, and W, right? And therefore, we choose a way of writing these products in this fashion, the way they will operate on a given vector. And then we can say VA is a product of linear transformations A and B, right? Now, if we have three linear transformations, let's say A, B, C, okay, then they will satisfy the associativity property. That means whether you do to explain this, I'll look at the transformations in this fashion. Let's say this is B vector space, this is U vector space, this is let's say W vector space, and let's say we define one more. I don't know what to call this now. Um, let's call it X, or let's call it Y. This is a Y vector space. Now there's a mapping happening from V to U using A, U to W using B, and B to Y using C. Now, based on the properties that, or the product definition that we have put, what we can say is you can define, what you can do is you can do first BA. This is essentially doing BA, and then you do C. Or you can have a product definition of operating between U, W, and Y. And there, in that case, this is going to be your CB. So you can do A first, and then you can do CB, direct mapping. So this essentially gives you the associativity property, correct? It also satisfies the distributivity property, which means that if you have, in this case, I should keep defining them as we go along. In this case, A, comma B are mapping, let's say, these are mappings. They belong to, let's say, A, comma B belong to the mapping, let's say V to U, the vector space V to vector space U. They belong to that. That's why you're adding them. Otherwise, you cannot add. If there is a mapping linear transformation which is mapping U to W, you cannot add it to V to U. So this addition is defined only for the same set of linear transformations that map from V to U or U to W, whichever, but then they have to belong to the same set of linear transformations, right? And let's say in this case, your uh, C is essentially that belongs to some transformation U to W, let's say. Of course, the way we have written it now, and we sort of maintain the order, so we call this as, let's call this W to U, sorry. Let's call it W to U. Now you have W here, and then U here, and oh, we have to say actually W to V, actually. W to V. See, this is why Venn diagrams are so useful, so that you don't make mistakes. U. So now this is a transformation C, and this is a transformation A and B, A comma B, right? So it comes from here, right? So in that case, you can separately map using A and B and then add them up, right? Now, clearly here, the way we have gone about it, it's sort of clear that this addition, if somebody would ask you, where is this addition? What is this vector addition? This vector addition is addition of vectors in, can you guess? It's going to be essentially U, right? Right. No, I think we have to check that here. Okay, this is not addition of vectors. Nope, nope. It's not addition of vectors. It's addition of linear transformations and belonging to which set? They're belonging to, you're taking a vector from W and mapping it to U. That's what this is. So this is addition of linear transformation from or in from basically the linear set of linear transformations W to U. Okay. Now let's look at the scaling. Lambda belongs to a field. It's a number. You can think of it mostly. You can think of field as a number, which is used for scaling. B times scaling of lambda is same as lambda times B of A, the way we define the product. So these are some of the properties. Now we look at some spatial transformations, and let's look at some of these. let's say we look at invertible transformations, which we call as isomorphisms. Okay. Now let's say consider a mapping. This mapping is from vector space V to vector space U. Okay. Now what you're doing is you're taking a vector V and mapping it to U, right? And you consider another mapping, which is mapping U to V. So A belongs to all the linear mappings B to U, and B belongs to the set of linear mappings or linear transformations from U to B, right? So that means if you take if you do the first mapping, that means you take a vector V and then map it using A, you'll get a vector U where U belongs to the vector space U. And going by the same thing, you have a mapping V, which B, which is mapping U to some vector B. If you can, if this mapping is possible, that means you map B to U using A, and then you have another mapping U given by mapping B to V. In that case, you have, if you would perform the take the product of these mappings, and that would mean that you're doing, let's say, V, U, and let's say V. So if we have mapping V to U, this is V, this is U, and then map U to again V using B. Okay. This would mean if you would have gone about the mapping in this fashion directly, that means B times A of V would always give you B. Okay. You can say that V of A is doing nothing but it's an identity mapping. So it maps the same vector to the same vector. That's why it's an identity mapping. Okay. So this identity mapping means that B essentially is can be called as the inverse of A. It's just inverting the mapping. You mapped V to U, and this mapping B, what it is doing is inverting the mapping. It's taking U and bringing it back to V. So this is called invertible. The B is called the inverse of A in that case. Right? B is the inverse of A. Now, normally we represent B as A inverse, and we call it invertible mapping or isomorphism, as I said. So, for when would this exist? This may not exist for all mappings A. This will exist only for some spatial mappings. And what is required? What you require is that A has to be a one-to-one and onto. Okay, we talked about what is one-to-one. That one-to-one means your K of A is just a zero vector, and onto means that the range of A is essentially same as the mapped space U. The mapped space is V, but the same as the space that we are mapping to. Okay, then you call, then you can say that A is going to be invertible. That means A inverse would exist. Okay, so if A is an one-to-one and onto mapping, then A is invertible. So there is another kind of mapping which is transpose of A, which is going to map U to V. But we'll talk about this later. Okay, this requires a special definition, and this is for define this transpose of A has some meaning for inner product spaces. So we'll talk about definition of transpose A or adjoint of A from that perspective. We'll do it later. Now consider a set of mappings in this fashion. Okay, you have a mapping A, which is mapping B to U, and another mapping B, which is mapping U to W, and both are one-to-one and onto mappings. Okay. That means they're invertible. That's what this means. So what you're doing is you have a vector space V and you're mapping using A to U, and then you have a vector space W and you're mapping U to W using transformation B, right? Now, if both are invertible, then it's possible that you can map B to U using this transformation B inverse. So B inverse belongs to the linear transformations from W to U, whereas B belongs to the linear transformations from U to W. Similarly, A belongs to the linear transformations from B to U, and A inverse belongs to the linear transformations from U to W, U to V, sorry. Correct? Right. So now from here you can say, so if you take a vector, let's say V, and you're looking at a mapping which is taking you directly to this guy, and you're using A and B for reaching there. So what you can do is you can think of it as a BA mapping, correct? So you take BA, it takes the vector V and gives you vector W. On the other hand, if you look at it from here, this is going to get mapped to directly to V. And what you're doing is essentially A inverse, B inverse, mapping W to U. Okay. So the inverse of B into A in that case from this you can guess is going to be same as A inverse B inverse. And that's the reason that you use this formula. That you have uh, to sort of when you write BA inverse, you get A inverse B inverse. The reason is the following, whatever we discussed here, right? As is given by this Venn diagram. Correct? Now, yeah. So in this lecture, till now, we have covered about, uh, of course, linear transformations. We talked about invertible linear transformations also. We talked about addition of linear transformation, product of linear transformations. And we looked at this special class of transformations, which are invertible transformations. Now we'll look at some more spatial transformations. Uh, and I think we have already talked about this just a minute ago, and that's the identity transformation. When we were talking about invertible transformations, I had mentioned something about the identity transformation. Now, identity transformation is nothing. It's essentially a transformation from V to V. And what it does is it takes a vector V and gives you a vector V back. So then this kind of a transformation is called, and this is true for every vector of the vector space V. Then you call that transformation as identity transformation. There is another kind of transformation which is a projection transformation. Okay. Or it has another name to it, idempotent transformation. And idempotent literally means same power. And you would know when we'll talk about, when we give the definition of projection transformation, you'll know why. So now this is defined. The projection transformation is again from a vector space V to the same vector space V, such that P square, if you do the transformation twice, okay, you do it once and then you again do it. That means you have V getting mapped using P, and then you again do this mapping. That means now you're doing this, going by the definition of products that we had transformations. What you're doing is here is P square, right? This is essentially P square. Now, if you say that P square is same as P, it means that once you had mapped a vector from this vector space V using P, you would have arrived somewhere at, let's say, V prime. Now, if you do P square, that's also same as doing 1 time P. That means here also you would arrive at V prime, right? So there is a special set of vectors v primes which belong to the range of P which get mapped to themselves. Okay. So in a way you can think of, you might have projected using this projection transformation, you would project a vector space V to a subspace of itself. Okay. Okay, you have projected that onto that. And then if you try to project that onto again using the same transformation, you will get the same set of vectors. That means it's going to be like an identity transformation beyond a point, right? For this subset of V. Now, if you do it twice or you do it n times, then it will have no effect. Okay, so it maintains its power. So p to the power n is going to be same as p for every n greater than equal to 2. So greater than equal to 2. Okay. Now let's try to understand it using an example, this kind of a transformation. Let's take a projection transformation from a 3D space to a 2D space. So you're uh, mapping it to a 3D space onto a plane. We'll call it V to V. Sorry, it's 3D to 3D, but as you will see that it will map it to 2D. So it's V to V only, it's 3D to 3D only, but it's going to, the mapping is going to bring it to a subspace of 3D. That's what we'll see. So let's define this projection Px as 1 as this matrix 1, 0, 0, 1, and the rest of the elements of the matrix are 0. Now, if you take any vector belonging to the 3D space, it'll get mapped to something like this, which essentially is going to be a subspace of 3D, and this essentially this belongs to 2D, right? So you have projected it to a subspace of 3D, which is 2D. Now this, if you do it this way, this is called an orthogonal projection, and the range of P in that case is same as R square, which is a subspace of R3, as I said. So if you want to see it graphically, what is happening? You have the axis XY axis like this in the 3D, and then let's say Z axis is pointing upward, this fashion, and you had a vector here which is X Y Z. Okay, given by this point. So this is a vector. Now, when you operated it over P, then what you get is P of X Y Z. I should not write it this way. Let's write it in a different way. P of X, Y, Z will map it to only the XY place. It will give you the coordinates. And this angle is going to be 90 degrees. Correct? And therefore it's called an orthogonal projection. That's why we named it as orthogonal projection. Now you can have an oblique projection also. We'll consider this example where projection transformation P is essentially from V to V, which is R square to R square. And we'll define it in this fashion, 0, 0 and alpha 1. And you can check when you do P square, as you have done here in this calculation. When you do P square, you'll get 0, 0, 0, 0, which gives you a 0 here. 0 into 0 into 0 is 0, and then this into this is again 0, so you get this 0. Then alpha into 0 and 1 into alpha, you get the alpha. And alpha times 0 and 1 times 1, you get 1. This is same as P. So this is a projection operator, right? So now when we operate on a 2D space with this projection operator, you get 0 times x is plus 0 times y is 0, and alpha times x plus y here. So if you would look at this projection graphically, as I've shown here in the picture below, you would see that graphically it will turn out to be something like you have the x-axis, you have the y-axis, and then you have the point x comma y here. Now, orthogonal projection would have meant that you go to y, but in this case, you're going to alpha times x plus y. So you're going in an oblique way. So this is not 90 degrees. So you call it oblique transformation. As simple as that. Now, we'll just briefly touch upon this final part and then stop. Uh, this theorem says that if P is a projection from V to V, then V is nothing but it's a direct sum of the range of P and the kernel space of P. So by saying that direct sum, what we mean is, if you would recall, range of P intersection K of P is essentially only zero vector. There is no overlap except for the zero vector. There is nothing, no vector in common between range of P and kernel space of P, and that's very clear. That's what's going to happen. Now, to prove this, what we do is, let's take a vector V belonging to vector space V. Now, U will be then P times V. U belongs to the range of P. Now, let's define a vector which is sort of from in which we are taking off the components of U. So, in a way, what we have done is we have removed U from it, from V, and you can write this as if you would try to write it as a sum of two transformations, you write this as I minus P times V operating on P, where I is the identity transformation. Now P times W, if you would do, will be P times I minus P times W, and if you will take the product of these transformations, you'll get P minus P square times W. Now P minus P square times W is essentially, P square is same as P as we have seen, so P square is P, and then essentially what you get is a zero transformation of W, mapping it to a zero always. Correct? That means if you would follow from here now, if you look at this, you will get that you can write V as this equation in this form also. You can write V as W plus P times V, and P times V is U, right? Belongs to the range of P. And as you can see, P of W is always zero. So P of W is always zero, correct? That means W belongs to, now since P of W is zero, it implies W belongs to kernel space of P, which is written here. Right. So, and this is true for any arbitrary vector. We have not sort of defined what vector we are looking at. This is for any vector V or from the vector space V. Now, that means you can write vector space V as a linear combination of a vector from kernel of K of P and range of P. That means the vector space V is then essentially a sum of range of P and kernel of P, these two subspaces. Now, to show that this decomposition is unique, that means this sum is a direct sum. In other words, it's a direct sum. That's what we want to show. And for that, we have to show that range of P intersection K of P should be zero. That is sort of seems obvious also in a way, but we'll prove it more systematically here. Let's say by contradiction, we'll prove it. Let's say U belongs to a range of P intersection K of P. Now, in that case, U is going to be equal to P times V, let's say. But then, because U belongs to K of P as well, that means P of U also is zero, right? Now we substitute U here in terms of V, so we'll get P of PV equal to zero, which would mean that P square V is P times V, which is same as U and is zero, which implies that u will be 0 is the only vector which belongs to range of P intersection of K with the kernel space of P. This 0 is the only vector, right? Which means we can write the vector space V as a direct sum of range of P and null space of P. Now, which this means that the dimension of V is same as dimension of range of P plus dimension of null space of P. That's what it means, right? All right. So we'll close this lecture here, and yeah, we can have questions now.